Interestingly, GJ1214b also serves as a case study in planetary migration. Its current orbit lies very close to its star, likely too close for it to have formed there. Instead, it probably originated farther out, in a cooler region of the protoplanetary disk, before migrating inward due to interactions with the disk or other planetary bodies. This inward migration might have profoundly altered its atmospheric composition and thermal profile, perhaps even stripping away lighter elements and leaving behind a denser, water-rich core surrounded by volatile gases. In this light, GJ1214b becomes more than a single point on an exoplanet chart. It becomes a narrative thread in the cosmic story of planetary motion and transformation. Its journey inward through the disk may have involved cataclysms and near collisions, tidal forces and radiative sculpting, reshaping its structure and destiny. Like a time capsule from an earlier epoch, it holds within its dense atmosphere the echoes of formation, migration, and evolution, processes that have unfolded over billions of years in silence and shadow. And yet, despite its opacity, despite the layers of cloud and gas that conceal its depths, GJ1214b speaks. It speaks through light and heat, through transit curves and emission spectra, through chemical fingerprints etched into photons that cross vast light-years to reach our instruments. We listen to it not with ears but with algorithms and detectors, decoding its silent message, one observation at a time. What GJ1214b ultimately teaches us is that the universe is not bound by our expectations. When we first looked to the stars in search of other worlds, we imagined Earth-like twins, rocky planets with blue skies and familiar conditions. But instead, we found GJ1214b, a dark, brooding world wrapped in a thick, impenetrable shroud, orbiting a faint, red sun. And yet, it is precisely because it defies our assumptions that it holds such scientific value. It invites us to expand our definitions, to widen the scope of habitability and planetary diversity, and to refine the models we use to describe the cosmos. In many ways, GJ1214b is a bridge between the known and the unknown. It exists at the edge of multiple transitions, from terrestrial to gaseous, from transparent to opaque, from simplicity to atmospheric complexity. It shows us how planets can evolve under conditions we had not fully considered, where water may not form oceans but instead exists in supercritical states, and where skies are not clear but eternally overcast with chemical mists and hazes. There's also an aesthetic dimension to this exoplanet, an almost poetic beauty in its unknowability. One can imagine a twilight world beneath a red star, cloaked in a global fog, its surface never visible, its secrets buried beneath layers of pressure and heat. A place where light struggles to penetrate and where the atmosphere itself becomes a vast, restless ocean. There is no land, no sea, just gradations of vapor and heat, a planetary canvas painted in grays and silvers, drifting in a quiet orbit through the interstellar dark. From a philosophical perspective, GJ1214b challenges us to confront our anthropocentrism. It reminds us that the cosmos is not constructed for our comfort, nor limited by terrestrial analogies. It whispers of planetary realities beyond human experience, where the rules of life, climate, and geology may be governed by entirely different balances of chemistry and physics. And in doing so, it deepens our sense of awe, not just at what we know, but at what remains beyond the veil. The pursuit of understanding GJ1214b, then, is not only a scientific endeavor, it is also an act of imagination, of empathy for the alien. As we build more powerful observatories and refine our techniques, We are gradually learning to listen more closely to such worlds, to hear the subtleties in their silent messages, and to piece together stories that were never meant for human ears, but that now, through light and intellect, can be heard across the void. As our instruments evolve and our questions deepen, GJ-1214b continues to stand at the frontier of exoplanetary science, a benchmark, a mystery, a mirror held up to our curiosity. It is a world that resists easy answers, forcing us to sharpen both our tools and our minds. Every observation it yields feels like a fragment of a larger puzzle, one that connects not just to this single exoplanet, but to a broader understanding of how planets breathe, evolve, and perhaps even perish. The mystery of its composition remains central. Is it a planet with a vast ocean buried beneath clouds of steam, heated by the relentless glare of its star and the crushing force of its own gravity? Or is it a mini-Neptune, with a dense atmosphere rich in hydrogen and helium, obscuring a rocky or icy core deep below? Both scenarios have profound implications for planetary classification. They speak to the need for a new vocabulary, new categories that go beyond the binary of Earth-like and Jupiter-like, for the universe, as GJ-1214b so clearly demonstrates, prefers a spectrum over simplicity. And there is another layer to the story: time. GJ-1214b is ancient. It has likely endured billions of years of stellar irradiation, orbital evolution, and internal transformation. The thick clouds that now block our view may be the product of eons of atmospheric escape and replenishment, a churning equilibrium between destruction and regeneration. If its atmosphere once held lighter elements, where did they go? If it is rich in volatiles now, how were they preserved? These questions connect the planet's present state to its deep past, forming a narrative arc of planetary aging, one that we are only beginning to trace. In time, GJ-1214b may also help us understand the broader demographics of exoplanets. It sits in a size range, the so-called radius valley, where relatively few planets exist. This apparent gap in the distribution of planetary sizes is thought to arise from atmospheric loss due to stellar radiation, splitting populations into smaller rocky planets and larger gas-rich ones. GJ-1214b's presence in this regime makes it a key data point, a potential exception that can illuminate the rule. Understanding why it retained such a thick atmosphere when others did not could tell us volumes about atmospheric retention, magnetic fields, and planetary survival. But beyond its physical characteristics, GJ-1214b represents something more enduring, a symbol of the transition we are undergoing as a species. For most of our history, the stars were distant, silent lights. Now, we can not only detect planets around them, we can read their climates, their histories, their chemical signatures. GJ-1214b, with its hidden depths and stubborn silence, is a teacher of patience and precision. It reminds us that discovery is not always revelation. Sometimes, it is the quiet persistence of returning, again and again, with better questions and sharper eyes. The narrative of GJ-1214b also carries an emotional weight, a resonance that comes from reaching across the stars and touching, however faintly, the reality of another world. It's not just a distant object catalogued by a telescope, it's a destination in thought, a place our minds can travel even if our bodies cannot. We map its temperature, its albedo, its orbital phase curve, not to control it, but to understand it, to welcome it into the expanding story of the cosmos we share. Each new dataset is a kind of translation, a rendering of alien conditions into human comprehension. We measure the flicker of starlight as it passes through vapor-laden skies, and from that flicker, we extract the fingerprints of molecules, the shadows of clouds, the heat of unseen surfaces. These are acts of translation across scales not just of distance, but of experience. GJ1214b is not for us, it was not built for our senses or our systems of meaning, and yet we persist in listening, in learning, in asking what it might be trying to say. In that way, the study of GJ1214b becomes an act of humility. It requires us to accept that most of what we encounter in the universe will not resemble Earth, and that strangeness is not deficiency. It is richness. It is nature's way of reminding us that creativity is not confined to our blue planet, and that reality is broader, more fluid, and more startling than we imagined. As missions continue, from the JWST to future concepts like Louvoir or HabEx, we will revisit GJ1214b with new eyes and deeper ambitions. Perhaps one day we'll resolve its atmosphere layer by layer, or simulate its interior down to the mineral. Perhaps we'll find isotopic anomalies that speak of long-lost oceans, or measure weather systems sweeping across its horizon in infrared. Perhaps, just perhaps, we'll find echoes of chemistry that hint at biological potential, even if only in the most primitive form. Or maybe not. Maybe GJ1214b will remain stubborn, elusive, always veiled. But even in that resistance, it will have done its work. It will have stretched us, taught us, inspired us to imagine worlds not as mirrors of our own, but as fully realized realms unto themselves. Worlds with their own physics, their own rhythms, their own impossible beauty. We learn that the pursuit of knowledge is not always about conquest or certainty. Sometimes, it's about reverence. About standing before the unknown and not demanding it yield, but instead asking how we might meet it on its own terms. GJ1214b is not a puzzle to be solved once and forgotten, it is a companion on the long journey of understanding, reminding us that the cosmos is not obliged to be legible, and yet it invites us to read. Even if we never see its surface, never glimpse its true colors or walk beneath its skies, the planet has already changed us. It has carved out a space in our scientific imagination, an icon of otherness, of complexity, of deep time and deeper mystery. It sits quietly in the catalogue of known exoplanets, and yet it echoes louder than many. Because it endures. Because it conceals. Because it offers no easy answers, only better questions. And what more fitting role for a planet than that? Not to serve as a replica or a replacement, but as a provocation, an invitation to think differently, to embrace complexity, to love the cosmos not for how it resembles us, but for how it challenges us to grow. In the end, GJ1214b is not just a distant world. It is a threshold. A marker of how far we've come in our ability to detect, infer, imagine, and connect. It shows us what is possible when science becomes a kind of listening, and curiosity becomes a bridge to the stars. It tells us, in its silent, clouded language, that the universe is wide, ancient, and filled with more forms of being than we can yet count. And still, we try. We reach out. We gather light. We build instruments delicate enough to catch the whispers of hidden worlds. And in doing so, we affirm something quiet and profound, that we are not alone in the cosmos, not because we found others like us, but because the very act of searching, of wondering, makes us part of something larger. The story of GJ1214b continues. It continues in the data streams sent from cold, silent telescopes orbiting high above Earth. It continues in the models running on glowing screens in university labs, simulating heat transport, cloud chemistry, and atmospheric escape. It continues in the minds of students who encounter this strange world for the first time and feel that spark of wonder, that sense of this is real, this is out there. A planet wrapped in mystery, circling a quiet red sun in the darkness, waiting. And perhaps that's the most beautiful part, it's still waiting. Not for us, specifically, but simply existing, indifferent to our questions, while we struggle to interpret its message. It's not the answer that matters most, it's the dialogue. The back and forth between observation and theory, between what we can measure and what we dare to imagine. Each transit, each spectrum, each new glimpse deepens the relationship. We may never know everything, but we'll always know more than we did before. In that sense, GJ1214b becomes a kind of cosmic koan, a paradox that both reveals and conceals, a world that teaches by withholding. It's a lesson in patience, in the slow unfolding of knowledge across generations. Just as ancient mariners once stared at unfamiliar constellations and wondered what lay beyond the sea, we now look to GJ1214b and wonder what lies beneath its clouds. Maybe that wonder is the whole point. Because in every unanswered question, in every failed model or puzzling observation, we find the edges of our understanding, and the invitation to push beyond them. GJ1214b is not just a scientific object. It's a direction. A vector pointing toward a future where knowledge is not a destination but a horizon. A world like a mirror held up not to reflect our image, but to show us how much we have yet to become. And so the planet turns, silently, beneath its red sun. A ghost in vapor, a promise in shadow, a lighthouse in the sea of stars. And so the planet turns, silently, beneath its red sun. A ghost in vapor, a promise in shadow, a lighthouse in the sea of stars. It orbits in silence, locked in a gravitational dance with its parent star, a red dwarf so faint we would not see it with the naked eye, and yet luminous enough to sculpt the chemistry of an entire world. That relationship, between star and planet, is intimate and enduring. GJ1214b is likely tidally locked, with one side forever scorched in perpetual day, and the other cloaked in eternal night. And between them, a terminator zone, a twilight frontier where heat and chemistry may meet in strange, ever-shifting equilibrium. There, alien winds might howl endlessly from light into darkness, dragging warmth across the divide, stirring thick clouds into a ceaseless storm. We don't know what it would be like to stand, if standing is even possible, within that atmosphere. Would it be dense enough to swim through? Would light penetrate at all, or would the sky remain a smothering, featureless gray? Would there be flashes of electrical activity, strange lightning in vaporous oceans suspended above crushing depths? Would the clouds glow with internal heat, casting dim radiance in a world without surface? And deeper still, beneath the atmosphere, what lies below? If GJ1214b is a water world, its ocean would not resemble anything we know. At pressures thousands of times greater than Earth's atmosphere, water may become exotic, superionic ice, with oxygen lattices and freely moving hydrogen ions, or fluid phases without clear distinction between liquid and gas. There may be no seafloor at all, just transitions of state, gradients of density and pressure, until, perhaps, a silicate or metallic core is reached, hidden beneath layers of unknown phase behavior. This planet, this strange and silent sphere, defies not only expectation but vocabulary. It demands new language, new metaphors. It is not a failed Earth or a mini Neptune. It is a GJ 1214b, a planetary identity entirely its own. That uniqueness is not a limitation but a gift. Because in learning to describe it, we learn to imagine more broadly. We realize that planets need not conform to our terrestrial intuition. That life, if it exists, may not bloom only on blue-green oases, but perhaps even within steamy, dense, high-pressure realms, drawing energy not from sunlight but from internal tides or chemistry, evolving into forms we would not yet recognize as alive. GJ 1214b also forces a re-evaluation of how we explore. No human probe will likely ever reach it. It is far beyond the reach of current propulsion, locked in a sky we can only observe from afar. And yet, our tools grow ever more precise. With James Webb, we can read its light like a book of shadows. With future missions, perhaps ones we have not yet dreamed, we may read its weather systems, track the seasonal chemistry of its atmosphere, and compare it to thousands of other mid-sized planets. Already, GJ 1214b has become a prototype in a new planetary taxonomy, one that includes hazy subneptunes, water-rich super-Earths, and cloudy intermediates. What began as a dim dip in stellar brightness has become an entire chapter in planetary science. It has launched papers, theories, simulations, even philosophical debate. It has reminded us that alien does not mean irrelevant, that the most instructive worlds may not be the most Earth-like, but the most other. And it has proven that a single planet, shrouded and distant, can transform our understanding of what planets are, and what they could be. GJ 1214b is the embodiment of the scientific process itself, a question with no final answer. A world that withholds, but not forever. Its silence is not rejection, it is an invitation. An invitation to listen better, to look closer, to reimagine what's possible. Every whisper of infrared light it sends is a syllable in a cosmic language we are just beginning to learn. And even if we never reach it, even if it remains a world hidden beneath its eternal clouds, it will have changed us. For in reaching toward it, in decoding its darkness, modeling its weather, contemplating its form, we have stretched the limits of our knowledge and deepened the well of our curiosity. And that is what exploration truly is. Not just the search for answers, but the cultivation of awe. So let the planet keep turning, invisible to the eye, luminous to the mind. Let it orbit in stillness, wrapped in vapor and enigma. We will continue to watch, to wonder, to listen. And someday, maybe not so far from now, we'll speak its name, not as a curiosity, but as an old friend in the sky, who showed us how vast, and how strange, and how beautiful, the universe can be. And in that recognition, of GJ 1214b not as a data point, but as a presence, we arrive at something profound. It is no longer just a planet, it becomes our planet, not in ownership, but in relationship. A companion in thought, in theory, in our collective unfolding understanding of what the cosmos contains and what it invites us to become. Every generation of scientists that turns its instruments toward it becomes part of a continuum, each spectrum, each model, each recalibrated theory, a thread in an ever-expanding tapestry of meaning. In the future, as exoplanet research matures and our catalogs swell into the tens of thousands, GJ 1214b will remain a keystone. A foundational world that marked a shift in planetary science, from detecting planets to decoding them, from simple classification to the nuanced art of atmospheric archaeology. It will serve as a benchmark for comparative climatology on worlds far beyond the solar system. How does cloud formation scale with gravity? How do photochemical hazes evolve around M-dwarf stars? How do atmospheric escape processes sculpt a planet over billions of years in a high-radiation environment? These aren't just technical questions. They're glimpses into planetary lives, into their childhoods in swirling disks of gas and dust, their migrations, their aging under starlight. GJ-1214b has endured the ultraviolet temper of a red dwarf for untold eons. Its atmosphere is not a static cloak, it's a record. A slow-motion diary written in vapor and light, archiving events across epochs we cannot yet visualize. Reading that record is like reading the history of weather on another world, one chapter at a time. But we may go even deeper. As planetary interior modeling advances, we may someday constrain not just the atmosphere of GJ-1214b, but its geological story. We may infer if it has plate tectonics, or a magnetic field, or a layered mantle beneath its crushing depths. We may ask whether heavy elements in its atmosphere were dredged up from within, and whether convection carries heat from a hot core, perhaps kept warm by radioactive decay or tidal forces. All these are components of planetary metabolism, not life, but the preconditions of a planet that is alive in its processes, in its complexity. And maybe, just maybe, in some distant future, when telescopes orbit worlds of their own and AI scientists whisper across quantum networks, someone will look back at GJ-1214b and see it not as a mystery, but as a milestone. The moment we first realized that worlds need not reflect us to teach us. That planets like this, enigmatic, clouded, half-known, can be just as essential to understanding life, the universe, and ourselves as any Earth twin. That will be its legacy. A planet without a face, yet one that reshaped how we see. A world without a surface, yet one that grounded our imagination. A distant, shrouded globe, circling a quiet star, that taught us how to listen through the static of cosmic silence, and find meaning in the patterns of light. And even as countless other exoplanets call out from the galactic dark, with clearer skies or more habitable zones, GJ-1214b will remain, serene, veiled, and enduring. Not just as a planet, but as a question. A mirror. A story. And the story continues. But perhaps the most tantalizing thought is this: what if GJ-1214b is not alone in its strangeness? What if it's the first whisper of a hidden population of planets, worlds cloaked in vapor and shadow, veiled not just in clouds but in complexity? What if we've stumbled upon an entire class of exoplanets, so unlike anything in our solar system that we've barely begun to recognize their patterns? GJ-1214b could be the Rosetta Stone of this unseen empire, an emissary from a realm of middle worlds, not terrestrial, not giant, but something else entirely. And if it is part of a population, what are they hiding? Are there deeper layers in those atmospheres, layers we cannot yet reach, where chemistry takes wild, unfamiliar turns? Could photochemistry in these steamy, high-pressure envelopes be producing exotic molecules, precursors to life, or to something stranger? With JWST, we're beginning to scratch the surface. But what if GJ-1214b is just the tip of a much darker, more intricate iceberg? What if some of these planets, bathed in the infrared glow of long-dead stars, wrapped in deep oceanic veils, have evolved biospheres not based on photosynthesis, but on something more alien. Chemosynthetic life in a pressurized soup of hydrogen and ammonia. Could whole ecosystems bloom in the twilight layers between heat and cold, day and night, never touching a solid surface? We don't know. That's what makes it thrilling. Because every time we think we've mapped the limits of planetary possibility, a world like GJ1214b arrives to remind us, the universe doesn't follow our rules. It writes its own. And here's where it gets even stranger: what if its atmosphere is changing? What if, buried in the subtle shifts in its light curve, are clues that the cloud cover is evolving, thinning, thickening, perhaps even cycling? Could GJ1214b have seasons, driven not by tilt but by chemical equilibrium, or volcanic outgassing deep below the clouds? Could we one day catch it mid-transition, its veil lifting slightly, just enough for us to glimpse something underneath? And what if, just for a moment, it looks back? Not in a conscious way, but in the eerie alignment of probabilities, in the way photons scatter just right, in the way an atmosphere whispers its composition to our detectors like a voice from a distant time. There's a moment, when the data comes in, when it feels almost like a dialogue, one not of words, but of light and gravity and possibility. In that moment, GJ1214b becomes something more than a planet. It becomes a threshold. To mystery. To fear. To awe. And what lies beyond that threshold, we are just beginning to imagine. And in that imagination, something shifts, something subtle, almost imperceptible, like a breeze moving through the halls of scientific certainty. GJ1214b is no longer just a point of interest on a sky map. It becomes a gravitational center in our minds, drawing in not only theories and equations but emotions, anticipation, curiosity, even a quiet sense of dread. Because what if the things we uncover on GJ1214b don't fit? What if the data we retrieve, those elegant absorption lines, those infrared shadows, start to tell a story that breaks our models? A chemistry we can't recreate in labs. A temperature profile that defies equilibrium. Variability in the atmosphere with no known source. What if GJ1214b isn't just complex, it's anomalous? What if, in some small, statistical sliver of possibility, it's impossible? And then, the whispers start, among researchers, among theorists. Not just about the planet itself, but what it means. If GJ1214b's formation couldn't have occurred under known planetary mechanisms, then what are we missing? Did it form elsewhere and migrate in an exotic way? Was it shaped by processes rare in our galaxy, or entirely unique? Could there be missing physics at play? Some begin to speculate: rogue stellar interactions, ancient collisions, or even the remnants of destroyed moons or failed binaries. Others ask darker questions, the kind usually left out of peer-reviewed journals: could a planet like this have been engineered? It sounds absurd. It should be absurd. But if one thing is certain in the era of exoplanets, it's that the universe loves to laugh at our definitions of normal. And what if GJ1214b is just the first? What if its cloud-covered kin are scattered across the galaxy, hiding in plain sight, planets whose signals we've dismissed as noise, whose spectra we've misread, whose stories we've silenced with our own assumptions? What if they're watching each other? Not through intelligence as we know it, but through gravitational resonance, energy transfer, or quantum-linked atmospheres, a slow, ancient communication system written in planetary behavior. What if these veiled worlds are part of a hidden network, not of life, but of pattern, of purpose? And we, accidentally, blindly, have begun to listen. We tuned in by chasing starlight. We built telescopes not to find meaning, but to measure temperature gradients and molecular bands. But what if meaning is what we stumbled into? And then, in some late-night lab, somewhere on Earth, a researcher sees something odd, a signal buried deep in the noise. Not a natural variation. Not a calibration error. A regularity. A repetition. A rhythm. It loops, not perfectly, but insistently. A pulse, perhaps. Or a pattern. She checks it again. And again. It's coming from GJ1214b. And it's not random. It's waiting. The signal is faint, barely above the noise floor, but it's persistent. Every few orbits, it returns, embedded deep in the planet's phase curve. Not in the brightness itself, but in the residuals, the difference between what we expect and what we see. Tiny fluctuations in light that shouldn't be there. Imperceptible shifts in timing. A pulse that threads itself through the noise like a breath through static. The researcher isolates it. Filters the data. Cross-correlates across multiple instruments, JWST, ground-based photometry, even archived Kepler and TESS light curves from a decade earlier. It's always been there. But no one noticed. Not until now. It repeats. Not in seconds. Not in minutes. In orbits. Every 6.472 Earth days, for orbits of GJ1214b, a faint pattern emerges. Something in the thermal emission changes. Not just cloud density or albedo. Something deeper. A brightness dip that doesn't correspond to the transit. An asymmetry in the infrared that drifts, but not chaotically. It's rhythmic. Coordinated. She doesn't publish right away. She double-checks everything. Then she sends it, quietly, to a few trusted colleagues. Astrophysicists. Data scientists. One cryptographer. They don't laugh. They run their own analyses. They scrub the data, blind to her conclusions, and still, they find it. The same harmonic anomaly. The same recurrence. They begin to call it the echo. But that's not what keeps them up at night. What haunts them is the shape. When mapped in 3 dimensions, using phase-space reconstructions and nonlinear filtering, the signal traces a strange curve. Not random noise. Not Gaussian deviation. A form. Fluid, elegant, recursive. Somewhere between a waveform and a fingerprint. And worse, it's not just from GJ1214b. The same form, distorted but recognizable, appears faintly in data from other cloud-shrouded worlds. K2-18b, TOI 1231b. Even the long-ignored HAT, P26b, worlds with thick atmospheres. Worlds we had written off as observationally impenetrable. Worlds that now, whisper back. It's not communication. Not in any language we know. But it feels intentional. An information structure, encoded not in radio waves or prime numbers, but in climate dynamics. in atmospheric phase shifts, in planetary entropy itself. A message written into weather. Or perhaps not a message at all, but a memory. And then the question emerges, not in a journal, not in a press release, but in the minds of those closest to the data, what kind of civilization encodes information not in metal or photons, but in the slow rhythms of planetary breath? What kind of presence would leave behind echoes not in structures or signals, but in atmospheres that remember? And if they exist, or once existed, what do they want us to find? GJ 1214b turns, cloaked and silent, but now, not quite alone. Its veil has shifted, just slightly. And what lies behind it is not a surface. Not an ocean. But something else. Something waiting to be remembered. The veil has shifted. And though the planet remains visually impenetrable, its surface lost beneath countless kilometers of vapor and pressure, the sense of presence has changed. Where once there was only opacity, now there is intrigue. Where once it was only a world we could not see, now it is a world we cannot look away from. The data spreads quietly at first. Shared in encrypted channels between teams across observatories and institutions. Discussions become more urgent, more abstract. Experts in atmospheric chemistry begin conversing with theorists of information entropy. Planetary dynamicists speak with astrobiologists and SETI researchers in late-night calls where the questions no longer feel theoretical. Because if the echo is real, if these patterns are not artifacts but artifacts of intention, then our assumptions about the universe must change. Perhaps intelligence, like life, is not always biological. Perhaps civilizations do not always build, transmit, and colonize. Perhaps some cultures, far older than ours, once lived on worlds like GJ 1214b, and chose another path. A quieter one. One not built of stone or signal, but of transformation. What if a species learned to manipulate the long-lived flows of its atmosphere? What if it chose to encode its thoughts, its histories, its memories into the phase transitions of clouds, into planetary scale oscillations, into the breath of the world itself? No monuments. No machines. Just storms that whisper the past in fractal patterns. Temperature shifts that murmur across centuries. A living planet as both mind and monument. And now, light years away, we listen. Not with radios. Not with rovers. But with patience. With algorithms. With silence. The final reports begin to circulate. The anomaly is confirmed. It is non-random. It is persistent. It is replicated across multiple planets. And though the interpretations vary, a consensus begins to form. This is not noise. This is structure. And then, just as quietly as it began, a question starts to echo back across humanity. Are these the remnants of someone who came before? Or are they a greeting? A doorway begins to open, not in space, but in thought. A widening of possibility. Of what it means to search. To find. To be in the universe. GJ 1214b continues its orbit, unchanged in its path, unchanged in its cloak of cloud. But now it is more than a world. It is a relic. A signal. A mirror. A story, half buried in vapor, unfolding across the light years like a dream too vast for a single species to hold alone. And somewhere, between the clouds and the silence, between entropy and memory, between now and a time we cannot yet name, it waits. And we, at last, are beginning to remember. Imagine stepping far beyond the bounds of our solar system, gliding past galaxies like flecks of stardust in a boundless sea. As you drift farther into the abyss, patterns begin to emerge, not in the stars themselves, but in the vastness between them. The universe, for all its chaos and randomness, is not a scatter of isolated galaxies in a void. It is a woven tapestry, a colossal structure so immense and interconnected that it challenges every human conception of scale, time, and reality. This is the cosmic web, the true architecture of the universe. At its core, the cosmic web is not made of stars or planets. It is made of gravity, time, and invisible matter. It is built from dark matter, the elusive, unseen mass that does not emit, reflect, or absorb light, yet governs the dance of galaxies across billions of light-years. Picture an intricate network of filaments stretching across space like threads of spider silk. Along these filaments, galaxies cluster like dewdrops, drawn by the pull of gravity into groups and superclusters. In between these filaments lie vast cosmic voids, empty expanses so enormous that entire galaxies pass through them like whispers in the dark. This structure was seeded in the earliest moments after the Big Bang, in a time when the universe was a hot, dense, uniform soup of particles and radiation. But even then, quantum fluctuations, tiny ripples in the energy field, planted the seeds of the structure we see today. Over billions of years, gravity amplified those fluctuations, pulling matter into denser regions and leaving behind yawning chasms. The result is a cosmic landscape sculpted by invisible forces, a silent scaffolding of dark matter upon which all luminous galaxies are hung. To map this hidden architecture, astronomers must act like cosmic cartographers, tracing the luminous beacons of galaxies to infer the dark skeleton beneath. Telescopes like the Sloan Digital Sky Survey have revealed sweeping arcs of galactic superclusters, each one spanning hundreds of millions of light-years. But even those are only fragments of a larger whole. Simulations of the universe, run on supercomputers using the laws of physics as their guide, reproduce these vast filaments with eerie precision, suggesting that our theoretical models are close, perhaps hauntingly so, to reality. And yet, even these simulations must make assumptions, about dark energy, about inflation, about the true nature of dark matter. Every parameter, every tweak, opens a different window into how the cosmic web might have evolved. It is a puzzle with missing pieces, some of which may never be found. The observable universe is only a fraction of the whole. Beyond our horizon, beyond the reach of light and time, the web may continue endlessly, looping back, fracturing, or birthing entire regions we will never see. But here, in our corner of the web, we are not isolated. Our Milky Way is not drifting aimlessly, it is part of a filament that connects to the Virgo supercluster, which itself is drawn toward the gravitational anomaly known as the Great Attractor. We are, quite literally, being pulled through the universe by invisible threads we cannot see, but whose influence shapes our fate. The very motion of our galaxy is evidence of the unseen structure around us. And through this all, we are left to ask, is the cosmic web just structure, or is it something more? Is it a skeleton, a circulatory system, a neural network? Is the universe thinking, in some unfathomable way, through these vast connections? We often compare the web to biological forms not out of whimsy, but because patterns repeat in nature. The same branching complexity found in neurons, in river systems, in tree roots, echoes in the structure of the cosmos. Is that a coincidence, or a clue? The idea that the universe might mirror the architecture of life itself is not just poetic, it is a natural consequence of the laws that govern complexity. From simplicity, order arises. From gravity, structure. From chaos, form. The cosmic web is not random. It follows a logic older than stars, a pattern etched into space-time by the unfolding of the universe itself. And yet, it is dynamic, alive in a sense. Galaxies do not simply sit still upon the filaments, they move, collide, merge. Like cells in a living body, they interact with their environment, exchanging matter and energy, altering the structure they inhabit. Streams of gas flow along these dark matter filaments, feeding galaxies like arteries delivering lifeblood. As galaxies consume this intergalactic medium, they ignite waves of star formation, burn through their resources, and then quiet down, only to be replenished again by the web. This cosmic cycle of nourishment and transformation is not isolated to one region, it is happening everywhere, across billions of light-years, in every direction. The web connects it all, and through it, the universe breathes. But what is this dark matter scaffolding made of? That remains one of the deepest mysteries in physics. It is not composed of atoms, nor of anything familiar from the periodic table. It interacts gravitationally, and that's almost all we know. Yet, it is this ghostly presence that dictates the layout of galaxies, bends the paths of light across space, and holds entire clusters together. Without it, the cosmic web would unravel. Stars would drift apart. Galaxies would never have formed. We owe our very existence to this invisible glue. And still, dark matter is only part of the story. Over the past 2 decades, we've discovered that the expansion of the universe is accelerating, driven by something even more mysterious, dark energy. If dark matter shapes the bones of the universe, then dark energy pushes its flesh outward, inflating space itself. Together, they form the yin and yang of cosmology, gravity pulling in, expansion pushing out. The cosmic web exists in the tension between these forces. It is not just a static map, but a dynamic battlefield between collapse and dispersal. What we see today is a frozen frame in a much longer film. The web is still evolving. Galaxies are still migrating. Clusters are still merging. Over the next billions of years, the filaments will stretch, grow thinner, perhaps snap. Galaxies will become more isolated as dark energy drives them apart, carried away on the swelling tide of spacetime. Eventually, the cosmic web may dissolve altogether, leaving only island universes in an ocean of darkness. But even then, its memory will remain, in the distribution of galaxies, in the trajectories of stars, in the whispers of background radiation. We are lucky, almost absurdly so, to exist at a time when we can observe the web, map it, study it. In a few trillion years, hypothetical observers might look out into the sky and see nothing at all. No filaments, no galaxies beyond their own. The cosmic web will have receded beyond the horizon of what is visible. The universe will appear static, lonely, deceptively small. Only by studying the cosmic web now, while we still can, do we have a chance to understand the true shape of everything. And still, that understanding is incomplete. We are specks on a speck orbiting a modest star in a typical galaxy on an ordinary filament of the web. Yet from this tiny vantage point, we have begun to unravel the structure of the cosmos. We've built machines to see the invisible, crafted simulations to test our theories, and stared into the night sky with a question that never truly leaves us: what is this all for? Perhaps the most humbling truth of all is that this web, the immense, ancient lattice of matter and emptiness, is not merely a backdrop to our existence. We are part of it. The atoms in our bodies were once stardust, forged in galaxies nestled along these filaments. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it emerged from stars that lived and died within this cosmic structure. The web is not just where we are; in some profound way, it is what we are. When we look into the web, we look into the past. Light from distant galaxies takes billions of years to reach us, painting a picture not of how things are, but of how they were. The deeper we peer, the younger the universe becomes. We can trace the filaments back through time, watching them form from the subtle ripples left in the cosmic microwave background, the afterglow of the Big Bang. These faint imprints, like fingerprints in the early universe, are the blueprints of the web we see today. And what a structure it is! Vast tendrils stretching across hundreds of millions of light-years, connecting galaxy clusters like nodes in a galactic brain. At the intersections, where multiple filaments cross, gravity reigns supreme. These are the birthplaces of giants, the densest clusters, the most massive galaxies, the deepest wells of gravity. The further you zoom out, the clearer it becomes that the universe is not homogeneous. It is patterned, organized, almost fractal in its complexity. And through it all runs the quiet hum of connectivity. Some astronomers wonder if the universe is, in fact, a kind of hologram, a projection of information encoded on a distant boundary. Others propose that space and time themselves are emergent, rising from even more fundamental relationships, perhaps from quantum entanglement, perhaps from information theory. If so, then the cosmic web might not only be a structure made of matter, but a network of relationships, a fabric of information stitched into reality. This would place us not merely in space, but within a vast informational matrix, where every node and connection is a piece of a universal computation. And as we trace this network, we are confronted by its elegance, its mystery, and its silence. The web does not speak. It does not shimmer or cry out. It simply is. Stretching from the beginning of time to the limits of what we can observe, it tells a story without words, a story of expansion, of gravity, of emergence and collapse, of light and shadow. It is a cosmic fingerprint, a signature of what the universe chooses to become when governed by simple laws and vast scales. We used to think that galaxies were the largest structures in the cosmos. Then we discovered clusters. Then superclusters. Then filaments. And then voids, gargantuan bubbles of near-nothing, bordered by shimmering walls of matter. With every step outward, the scale changed, and with it, our place in the story. We are not at the center. We are not even on the edge. We are part of the weave itself, one thread in a fabric too vast to hold in the mind. And yet, we can map it. We can model it. We can dream of it. That might be the greatest paradox of all, that consciousness, arising from fragile biological matter on a tiny world, can reach out across billions of light-years and perceive a structure it did not create but is somehow a part of. The web, silent and indifferent, becomes knowable through us. And in doing so, it reflects something back, not a purpose, not a message, but a mirror. Perhaps this mirror, held up by the cosmos, is not meant to answer us but to reveal us, to reflect back the strangeness of our existence, the impossibility of our awareness in a universe so vast and ancient. When we look into the cosmic web, we are not just studying galaxies or particles of dark matter, we are watching the stage on which every moment of cosmic evolution has unfolded. Every gravitational collapse, every burst of star formation, every supernova and quasar flare, all of it choreographed along the delicate threads of the web. And somehow, impossibly, within one of these galaxies, within one of its stars orbiting rocks, emerged minds curious enough to trace the filaments and wonder why they are there. It's not just the presence of structure that is remarkable, it is that the structure can be known. That mathematics, scribbled in chalk or encoded in silicon, can describe the shape of the unseen. That equations born in human thought can model structures spanning the observable universe. This is not coincidence, this is the resonance between reality and the mind's ability to model it. And what is the web becoming? It is not frozen. Every moment, gravity continues to weave, dark energy continues to stretch. Voids expand. Filaments thin. Clusters tighten. Collisions erupt. Time does not stop. In the grandest of timescales, even the cosmic web has a life cycle. It was born in the primordial plasma. It grew through gravity's patient sculpting. It matured into the filaments we observe today. But it will age. It will change. Perhaps it will tear. Eventually, if dark energy continues its relentless acceleration, the distances between nodes of the web will grow so vast that light itself will no longer bridge the gaps. Information will cease to travel. Cosmic isolation will deepen. In some far future, the web may remain only as local memory, a whisper of gravity locked inside ancient galaxies. The grand architecture we now map and marvel at will fade into blackness, not because it disappears, but because it moves beyond reach. And yet, the cosmic web is not only about what is out there. It is also a symbol, of connection, of emergence, of order within the deep unknown. It hints that even amid darkness, patterns form. That gravity, the most patient of forces, can take the chaos of the early universe and turn it into something as organized as a filament of galaxies threading through space. It is a reminder that the universe is not static, not simple, not empty. It is layered, alive with structure, in constant flux. In our mythologies, we often speak of webs, the threads of fate, the loom of time, the interconnectedness of life. Now we find that science, in its cold precision, returns us to the same metaphor. The universe is woven. It is a vast loom of gravity and dark matter and energy. And we, improbably, are the brief sparks of awareness glowing in its strands. There is something hauntingly beautiful in the idea that the universe, for all its coldness and silence, creates patterns so intricate they mirror thought itself. The cosmic web, with its nodes and filaments, has become more than a structure, it is a metaphor, a lens through which we begin to see not just the universe, but the shape of knowledge, the architecture of emergence, the flow of complexity. Its very existence challenges the notion that randomness reigns. Somewhere between entropy and order, between expansion and collapse, the web takes form, not imposed from without, but arising from within, through the unfolding of cosmic laws written in the language of gravity and time. We are used to thinking of galaxies as isolated islands, grand and luminous. But this view is incomplete. Galaxies are not solitary. They are bound to each other through invisible tethers of dark matter, moving as constellations within a greater structure. They fall toward one another, they stretch into tidal bridges, they dance and merge and sometimes vanish into silence. In this way, the web is not only a static map, it is choreography. Every filament is a current. Every node is a memory. Some regions of the web are crowded, clusters upon clusters, where matter is dense and hot and turbulent. Others are vast voids, where galaxies are few and silence reigns. These contrasts tell a deeper story, that the universe, though governed by universal laws, is not uniform. It has character, texture, memory. Some parts evolved rapidly, forming galaxies early, while others slept through eons, forming stars only slowly. This unevenness is not noise, it is history. The web records every fluctuation from the early universe, every fold and wave, stretched out across billions of years like cosmic sediment. What, then, is the cosmic web telling us? That there is a larger order than what we see in the night sky. That the universe is more than a collection of galaxies scattered by chance. That there is a framework, unseen but real, upon which all visible matter is arranged. And perhaps most profoundly, that we live not at the end of this structure, nor at its beginning, but inside it. We are immersed within the threads, like neurons in a mind, like drops in a stream. And we are only just beginning to see it clearly. With instruments like the James Webb Space Telescope, Euclid, and future cosmic surveys, we are mapping more of the web than ever before, not just its galaxies, but its gas flows, its faint lensing effects, its temperature gradients. We are detecting the intergalactic medium glowing faintly along filaments, the whispers of baryons stretched between galaxies, the shock waves of structure formation echoing through the cosmic medium. Every photon we catch is a clue. Every map we create is a step toward understanding the largest story ever told. And yet, for all we know, we still stand at the edge of comprehension. What lies beyond the web? Are there deeper layers, hidden dimensions, unseen symmetries? Is the cosmic web a final structure, or merely the surface tension of a much vaster and stranger cosmos, one that twists beyond our mathematics and sensory tools? We do not know. But the web invites us to keep asking, to keep tracing its threads into the darkness. And so we follow those threads, across time, across space, across the boundaries of what we thought we could know. Each new observation, each refined simulation, each unexpected anomaly adds another stitch to the vast embroidery of cosmic understanding. But like any true web, the closer we look, the more it reveals layers we hadn't seen before. What once seemed solid and defined blurs into fluid complexity. Filaments are not simple lines, they are braided structures, composed of smaller strands of gas, dark matter, plasma, and galaxies coiling and twisting like cosmic ropes under tension. Some of these filaments carry currents, literal rivers of matter flowing between clusters. Others act like conduits of magnetism and heat, transporting not just particles but information. They are not empty highways. They are dynamic environments where galaxies grow, evolve, and sometimes die. And between these cosmic highways lie the voids, not dead zones, but regions of astonishing silence and equilibrium, where galaxies drift with a kind of inertia, untouched by the rush of gravity's great engines. It is within these voids and filaments that nature conducts its grandest experiments. Gravity, pressure, and temperature sculpt matter on scales that dwarf imagination. Here, massive galaxies spin like gyroscopes, their motion dictated not by local gravity alone, but by the shape of the web itself. These filaments have directionality, they guide matter, they channel collapse, they steer the flow of evolution. In this way, the cosmic web is not just a backdrop to galactic history. It is the architect. And yet, we are discovering that even this grand design is more subtle than we ever thought. Recent studies suggest that the orientation of galaxies is not random, they spin in alignment with the filaments they inhabit. Like dancers moving in rhythm with invisible music, galaxies seem to twirl in harmony with the structure around them. This suggests a memory of formation, a fossil record of flow, an echo of the early universe preserved in the shape and spin of galaxies today. But the web is not immutable. It is shaped by feedback. When galaxies form stars too quickly, they erupt with supernovae and winds that ripple back into the web, altering its pressure, its chemistry, even its topology. When black holes awaken in galactic centers, they blast jets of energy into the filaments, carving cavities in the intergalactic medium, pushing matter away, sometimes even cutting off future galaxy formation. The web listens. It reacts. It adapts. This is not a static framework, it is a system. A system that remembers. Even now, light from ancient collisions is still traveling through the web, crossing voids, bending around mass, finally arriving at our telescopes as a whisper from a time before Earth had oceans. These photons are messengers of entropy, of structure, of time itself. They tell us that the web is not a moment, it is a process. It is history woven into geometry. It is the past still unfolding into the present. And perhaps that's the deepest truth the cosmic web offers us, not just that the universe has structure, but that it wants to structure itself. That out of chaos, order will emerge. That gravity will bind, time will evolve, and space will stretch into meaning. In every strand, we see that process unfold. And in understanding it, we begin to understand ourselves, as observers, as participants, as temporary knots in a fabric that stretches far beyond our sight. Absolutely, let's deepen the scientific core, enrich it with theories, models, and the fascinating phenomena that make the cosmic web one of the most extraordinary ideas in all of cosmology. To truly understand how the cosmic web emerged, we must look back nearly 13.8 billion years to the moment of the Big Bang. In those first fractions of a second, the universe was not just hot and dense, it was quantum. Fluctuations on subatomic scales, born of Heisenberg's uncertainty principle, were stretched across cosmic dimensions by a process known as inflation. This rapid exponential expansion didn't just make the universe large, it seeded it with the blueprint of structure. These quantum fluctuations became density variations, some regions slightly more dense, some slightly less. Gravity seized on these differences. Over time, denser regions grew denser, pulling in matter, while less dense regions emptied, forming voids. This fundamental instability, Jean's instability, is what drives the universe's matter to cluster. The result? A cosmic scaffolding built on dark matter and modulated by baryonic, normal, matter. Modern simulations such as Illustris, Eagle, and Millennium use these early conditions to evolve the universe forward using general relativity and fluid dynamics. These simulations, containing billions of particles representing dark matter, gas, and stars, recreate the cosmic web with uncanny accuracy. They show that galaxies are not scattered like crumbs on a table, they flow along filaments, form at intersections, and die in isolated pockets of emptiness. This reproduction is one of the greatest triumphs of lambda CDM, lambda cold dark matter, the standard model of cosmology. The lambda refers to dark energy, the mysterious force that is accelerating the expansion of the universe. In this framework, cold dark matter, non-relativistic and slow-moving, clumps under gravity to form the web. But we don't directly see this web. We infer it through gravitational lensing, galaxy redshift surveys, and the intergalactic medium. Gravitational lensing is especially powerful. As light from distant galaxies passes through a filament or a cluster, it bends around the mass due to spacetime curvature, revealing the hidden presence of dark matter. Through weak lensing, tiny distortions in galaxy shapes, we map the contours of the web, like wind revealing the shape of an invisible mountain. And then there's the Lyman alpha forest, a series of absorption lines in the spectra of distant quasars, caused by clouds of hydrogen gas tracing the cosmic web. Each dip in the spectrum marks a denser region between us and the quasar, like counting tree rings to read a forest's history. These data let us reconstruct the three-dimensional shape of filaments across the observable universe. Even more fascinating is the role of cosmic magnetism. Though often ignored in early models, recent studies suggest that filaments may carry intergalactic magnetic fields, stretched and amplified by the flows of gas and shockwaves of structure formation. These fields, while weak, influence the motion of cosmic rays and the orientation of galactic jets, hinting at a magnetic skeleton beneath the visible cosmos. Another critical element is baryon cycling. The intergalactic medium, which forms the bulk of the web's visible matter, is a dynamic ecosystem. Galaxies pull in gas along filaments, ignite in starbursts, and then eject enriched matter back into the web via supernova-driven winds and active galactic nuclei. This cycle of inflow and outflow not only seeds future generations of stars, but chemically enriches the filaments themselves with heavy elements, carbon, oxygen, iron. The web becomes not just structure, but a highway of life's raw materials. Meanwhile, the anisotropy of the cosmic microwave background, CMB, the oldest light in the universe, offers direct evidence of the web's early skeleton. Instruments like Planck and WMAP measure temperature fluctuations across the sky, which correspond to regions of differing density in the early universe. These subtle patterns match the locations of today's filaments and voids, confirming that the cosmic web is an echo of the very beginning. As our models improve, we begin to consider more exotic possibilities. Could dark matter be self-interacting, changing the density profile of filaments? Could the neutrino background influence small-scale structure in the web? What role does modified gravity play, if general relativity breaks down at cosmic scales? These are not fringe questions, they are at the frontier of theoretical physics. Some theorists even explore topological defects left over from symmetry breaking in the early universe, cosmic strings, domain walls, textures, as possible influences on the web's morphology. These hypothetical features, if real, could twist the geometry of spacetime and imprint themselves into the pattern of large-scale structure. And then comes the question of cosmic homogeneity. On the largest scales, is the universe truly uniform? Or are there supervoids and superstructures, immense deviations from average density, that challenge our understanding of cosmology itself? Observations of the cold spot in the CMB or the Hercules, Corona Borealis Great Wall, a structure spanning over 10 billion light-years, suggest we may still be missing something. Let us dive deeper still, into the tensions, paradoxes, and edge cases of our cosmological model, where the cosmic web doesn't just inspire awe, but poses profound questions about the fate of the universe, and the physics that might lie beyond what we know. One of the great puzzles of modern cosmology is the Hubble tension, a growing discrepancy between the rate of cosmic expansion as measured from the early universe, using the cosmic microwave background, and the rate measured from the local universe, using supernovae and standard candles. The early universe method, grounded in lambda CDM, suggests a slower expansion rate, while local measurements yield a faster one. This isn't a small difference, it's persistent, statistically significant, and unresolved. And if the tension holds, it may point to new physics beyond the current model. Some theories suggest that the discrepancy could arise from early dark energy, a transient field that temporarily sped up expansion before dark energy as we know it took over. Others posit interactions between dark matter and dark energy, or variations in the neutrino sector, perhaps the existence of sterile neutrinos that leave subtle imprints on the growth of the cosmic web. This brings us to another critical concept, the growth rate of structure. If dark energy is simply Einstein's cosmological constant, lambda, then the web should evolve in a predictable way, filaments growing more slowly as expansion accelerates. But what if observations show otherwise? If filaments are growing faster or slower than expected, it could hint at modified gravity, alternative theories like F.R. gravity, scalar, tensor models, or even emergent gravity. Each one reshapes the very laws that govern the web's evolution, and each one offers a different vision of what the universe is made of. Some theorists, like Eric Verland, propose that gravity is not a fundamental force, but an emergent phenomenon, an entropic force arising from the statistical behavior of microscopic degrees of freedom. In such a view, dark matter may not exist as particles, but as a manifestation of information gradients within spacetime. This radically reconceptualizes the web, not as matter clumping in a vacuum, but as geometry responding to entropy and information. Meanwhile, observational cosmology is pushing the limits of what we can resolve. Projects like Euclid, DESI, and the Vera Rubin Observatory are preparing to map billions of galaxies with unprecedented precision, tracing the filaments, voids, and flows in exquisite 3D detail. These surveys don't just show where galaxies are, they measure how they move, how they clump, how they lens background light. They will test the very bones of the cosmic web. One particularly exciting frontier is redshift space distortions, where the peculiar velocities of galaxies, due to gravitational infall into filaments and nodes, cause deviations in their redshift. These distortions give us a way to measure gravity on cosmological scales, and to test whether general relativity holds across the vast fabric of the web. There is also the emerging science of void cosmology. Once considered uninteresting, cosmic voids are now recognized as powerful laboratories for testing cosmological models. Because they are underdense, they amplify the effects of dark energy and modified gravity. Any deviation from expected expansion or clustering shows up clearly in their evolution. By studying the motion of galaxies in and around voids, we can probe the very elasticity of spacetime. And then there is the question of cosmic fate. As dark energy dominates more and more of the energy density of the universe, the web's growth will freeze. Galaxies will no longer merge. Filaments will thin. Clusters will become gravitationally isolated, island universes, drifting in accelerating emptiness. Over trillions of years, even the web itself will fade, leaving behind a ghost of structure in the cold and the dark. Some models propose more extreme endings: the Big Rip, where dark energy tears apart not just the web, but galaxies, stars, and eventually atoms themselves. Others imagine a cyclic universe, where the web collapses and reforms in an eternal loop. And some venture beyond spacetime entirely, into multiverses, higher-dimensional branes, or simulations, where the web we see is just one thread among countless others, woven through realities we can scarcely imagine. And still we return to the observation: in all its vastness and strangeness, the web works. Galaxies form where the simulations say they should. Gravity bends light as predicted. Filaments emerge from quantum noise with breathtaking consistency. For now, Lambda CDM reigns, not because it is perfect, but because it explains more with less than any model before it. Let us now venture into the quantum deep, into the origin of the cosmic web, not just as a structure of matter, but as a crystallization of fluctuations in a newborn quantum universe, where spacetime itself was in flux, and where the seeds of structure were not drawn with particles, but with probabilities. In the earliest sliver of time, less than 10⁻36 10⁻36 10⁻36 seconds after the Big Bang, the universe underwent a phase of cosmic inflation. During this epoch, space expanded faster than the speed of light, stretching quantum fluctuations to macroscopic scales. These fluctuations were not like ripples in water, they were uncertainty itself, minute variations in energy density born from the strange realm of quantum field theory, where empty space is never truly empty. In this foamy, probabilistic sea, random differences in the vacuum's energy density gave rise to pockets of slightly more matter, slightly more gravity. As inflation ended and the universe transitioned into a hot, dense plasma, these differences were locked in, like frozen vibrations in spacetime itself. This quantum randomness became the cosmic blueprint. Without it, the web would never have formed. There would be no clusters, no stars, no planets, no observers to ponder it. These early fluctuations are beautifully preserved in the cosmic microwave background, a snapshot of the universe when it was just 380,000 years old. Tiny temperature differences in the CMB, only 1 part in 100,000, map directly to density differences in the early universe. These are the ghostly imprints of the quantum foam, now expanded across billions of light-years. And yet, they are not truly random. They follow a near-perfect scale-invariant power spectrum, predicted by inflationary theory. Larger fluctuations are rarer, smaller ones more common, but all are linked by a universal pattern. This self-similarity is echoed in the web structure, filaments and voids appearing at all scales, from galactic groups to superclusters. It's as if the early universe whispered a single equation, and gravity spent 13 billion years singing it into form. But what lies beneath even that equation? Some physicists argue that space and time themselves may not be fundamental. In frameworks like loop quantum gravity or string theory, spacetime emerges from deeper entities, vibrating strings, spin networks, or abstract information structures. In this view, the cosmic web is not a network of matter within space, it is space, shaped by the entanglement patterns of a deeper quantum reality. Indeed, recent advances in quantum gravity and AD/CFT correspondence suggest that entanglement, the quantum linking of particles across space, may be the scaffolding from which spacetime itself emerges. The structure of the universe, including the cosmic web, may then be a projection of more fundamental informational relationships. In this radical interpretation, what we see as dark matter filaments and baryonic flows could be shadows, holographic projections, of computations happening at a deeper level of physical law. Could the cosmic web be a kind of neural network, not metaphorically, but literally, a structure formed from entangled quantum states, processing information as it evolves? Some researchers have even compared the topology of the cosmic web to that of biological brains. Both exhibit small world networks, clustered nodes, hierarchical organization. Though speculative, it invites the question, does complexity naturally evolve toward similar architectures, whether in matter, biology, or the cosmos itself? If so, might consciousness, this flicker of awareness inside our neural webs, be an echo of the greater web we inhabit? Might our own brains, evolved within the filaments of galaxies, reflect the very patterns from which they arose? Not in mysticism, but in mathematical resonance, an alignment between the principles of structure, flow, and self-organization across vastly different scales. This brings us to a philosophical horizon. If the universe is governed by patterns that repeat, if structure emerges wherever systems are given time and freedom to evolve, then perhaps the cosmic web is not just a consequence of physics, but a cosmic archetype. A recurring solution to the fundamental equations of reality. A scaffold not just of matter, but of possibility. In this sense, the cosmic web is not only where the universe is, it may be a glimpse of what the universe wants to be. An attractor in the phase space of all possible realities. A structure that arises because it must. Because gravity curves. Because entropy spreads. Because time flows. Shall we now journey further into time's future, into the slow unraveling of the web, or trace its influence on the birth of stars, galaxies, and the conditions for life itself? And so we return to where we began, not with answers, but with a deeper sense of awe. The cosmic web is more than the structure of matter. It is the unfolding of the universe's memory. It is the silent architecture of everything that has ever happened and everything that will. Each filament is a thread of time, stretching from the earliest whispers of quantum fluctuation to the grand collisions of galaxies still yet to occur. Each void is a vast pause in the cosmic symphony, a resting breath between movements of starbirth and collapse. The web is not just the space between galaxies, it is the rhythm of cosmic becoming. Galaxies form and dissolve along these threads. Stars ignite, live, and die. Black holes spin silently in the nodes of gravity's deep well. And somewhere, in the filaments of a modest spiral galaxy, a species of conscious matter arises and dares to look outward, to question, to simulate, to understand. That we are able to even speak of the cosmic web is itself a miracle, a proof that the universe can become aware of itself. Yet the web, too, is mortal. As dark energy drives galaxies apart and silences the gravitational conversations between clusters, the threads will stretch and dim. In some distant epoch, perhaps 100 trillion years from now, the cosmic web will fade beyond visibility. The last galaxies will shimmer like fireflies in a fog. The universe will slip into the degenerate era, where stars no longer form, black holes slowly evaporate, and matter collapses into cold, dead remnants. The grand architecture will remain in fossil form, ghost filaments etched in the velocity dispersions of ancient stars, in the anisotropies of background radiation, in the faint whisper of gravitational waves echoing across eternity. But that time has not yet come. We live in the golden age of structure, in a universe richly webbed, where galaxies flow, stars burn bright, and minds awaken. We are latecomers to the party, yes, but just early enough to still read the story written in the stars. Our telescopes, our simulations, our equations, they are how we trace the spine of the cosmos. They are how we remember the beginning. And perhaps, how we shape the future. For the cosmic web is not finished. It is still forming, still changing, still reacting to the presence of matter, of energy, of feedback from the very galaxies it created. There is still time. The web breathes, and we breathe with it. It has no center, no edge, no final destination, only an endless unfolding of complexity and connection. And if we are wise, we will continue to listen to its language, the gravity of silence, the light of ancient stars, the geometry of emergence. Because in understanding the web, we are not just mapping the universe, we are learning to see the invisible, to trace order in chaos, to find meaning in the vastness. We are learning, in the deepest sense, what it means to belong to something immeasurably greater than ourselves. The cosmic web is not only the structure of the universe. It is the universe. And we are part of it. Gravitational wave astronomy is a rapidly evolving field that has transformed our understanding of the universe by providing a new way of observing some of its most extreme and energetic phenomena. Unlike electromagnetic radiation, gravitational waves are ripples in the very fabric of spacetime itself, predicted over a century ago by Albert Einstein's general theory of relativity. These waves are generated by the acceleration of massive objects, particularly in systems involving black holes, neutron stars, and other compact bodies undergoing violent interactions. The first direct detection of gravitational waves occurred in 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, observed the merger of two stellar mass black holes approximately 1.3 billion light-years away. This groundbreaking discovery not only confirmed a major prediction of Einstein's theory but also marked the beginning of gravitational wave astronomy as a fully operational branch of observational astrophysics. Since then, LIGO, together with its European counterpart Virgo and more recently CAGRA in Japan, has detected dozens of such events, opening an entirely new window into the cosmos. Gravitational waves carry information about their sources that cannot be obtained through traditional electromagnetic observations. Because they interact very weakly with matter, they can travel vast cosmological distances without being absorbed or scattered, arriving at Earth nearly unaltered. This makes them ideal messengers for probing the most hidden and energetic processes in the universe, such as the coalescence of black holes or the inner mechanics of neutron-star mergers. These waves are detected through laser interferometry, a technique that measures the minuscule distortions in spacetime caused by passing gravitational waves. The detectors consist of long perpendicular arms, several kilometers in length, through which laser beams are bounced between mirrors. A passing gravitational wave changes the relative lengths of these arms by an amount as small as 1/10,000th the diameter of a proton. Advanced technologies such as vibration isolation, ultra-high vacuum systems, and quantum-enhanced optics are required to detect such tiny signals against a background of terrestrial noise. One of the most significant events observed to date is GW 170817, the merger of two neutron stars detected in 2017. This event was not only seen in gravitational waves but also in gamma rays, X-rays, optical light, and radio waves, marking the birth of multi-messenger astronomy. The combination of gravitational and electromagnetic observations allowed astronomers to pinpoint the location of the merger, study the ejected matter, confirm the origin of heavy elements such as gold and platinum, and refine measurements of the Hubble constant. Gravitational wave observations have also provided insights into the population and formation channels of compact objects. By measuring the masses and spins of black holes involved in mergers, scientists can infer their likely origins, whether they formed through isolated binary evolution or dynamical interactions in dense stellar environments like globular clusters. Some detected black holes have masses that fall into the so-called mass gap, challenging previous models of stellar evolution and supernova physics. Beyond astrophysical sources, gravitational wave astronomy also has the potential to probe the early universe and test fundamental physics. Primordial gravitational waves generated during cosmic inflation, if detected, would provide a direct glimpse into processes occurring a fraction of a second after the Big Bang. Furthermore, precise measurements of waveforms allow for stringent tests of general relativity in the strong field regime, potentially revealing deviations that could hint at new physics or modifications to our understanding of gravity. As gravitational wave detectors become more sensitive and new facilities come online, such as the Einstein Telescope in Europe and the Cosmic Explorer in the United States, the future of the field looks extraordinarily promising. These next-generation observatories aim to extend the detection horizon to redshifts beyond 10, enabling the study of black hole and neutron star mergers throughout the history of the universe. At the same time, space-based missions like the Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will target lower-frequency gravitational waves from supermassive black hole mergers and other exotic sources, further expanding the gravitational wave spectrum accessible to human observation. In addition to probing astrophysical events, gravitational wave astronomy serves as a powerful tool for exploring the nature of spacetime itself. By analyzing the polarization, dispersion, and speed of gravitational waves, researchers can test the fundamental assumptions of general relativity and search for signs of alternative theories of gravity. For instance, any observed deviation in the propagation speed of gravitational waves compared to that of light could point to the existence of extra dimensions, violations of Lorentz invariance, or the presence of massive gravitons, hypothetical particles that mediate the gravitational force. Another exciting application of gravitational wave astronomy is the ability to use compact binary coalescences as standard sirens. Analogous to standard candles in electromagnetic astronomy, these events have predictable gravitational waveforms that can be used to measure the luminosity distance to the source. When combined with redshift information obtained from electromagnetic counterparts or host galaxies, standard sirens provide an independent method for determining cosmological parameters, including the Hubble constant and the equation of state of dark energy. This has led to new insights into the current tension between different measurements of the Hubble constant and offers the promise of resolving this discrepancy in the future. The field also contributes to our understanding of nuclear physics under extreme conditions. Neutron star mergers offer a unique laboratory for studying matter at supernuclear densities, where the behavior of nuclear matter is governed by the poorly understood equation of state. The post-merger signal, if detected with sufficient sensitivity, can reveal details about the internal composition and structure of neutron stars, including the possible existence of exotic states of matter such as hyperons, deconfined quarks, or color superconducting phases. Observations of tidal deformability, the extent to which a neutron star is distorted by its companion's gravitational field, also provide constraints on these models. In the broader context of astrophysics, gravitational wave detections are helping to refine models of stellar evolution, binary formation, and the life cycle of massive stars. They have revealed the existence of surprisingly heavy stellar mass black holes, with masses exceeding 30 solar masses, objects that challenge previous expectations about mass loss during stellar evolution and the metallicity dependence of black hole formation. Some detections have also shown evidence of eccentric or misaligned spins, suggesting that not all mergers occur in isolated binary systems, but may result from complex interactions in dynamically active environments such as nuclear star clusters or the accretion disks of active galactic nuclei. As the catalog of gravitational wave events grows, machine learning and advanced statistical techniques are playing an increasingly important role in data analysis. From real-time event detection to parameter estimation and signal classification, artificial intelligence is enabling faster and more accurate interpretation of the vast streams of data produced by modern interferometers. These tools are essential not only for identifying weak or overlapping signals, but also for distinguishing true astrophysical events from spurious noise and instrumental artifacts. Moreover, gravitational wave astronomy is becoming deeply interdisciplinary. It connects with particle physics, quantum optics, computational science, cosmology, and even philosophy. The detection of gravitational waves from cosmic strings, phase transitions in the early universe, or exotic objects like boson stars could reveal physics beyond the standard model. Simultaneously, the need for ever more precise measurements has driven technological innovation in areas such as squeezed light generation, cryogenic cooling, and precision metrology, with potential applications far beyond astronomy. The future of gravitational wave astronomy is marked by a shift toward observing a broader and more diverse gravitational wave spectrum, encompassing both lower and higher frequencies than currently accessible. Ground-based detectors like LIGO, Virgo, CAGRA, and their successors are most sensitive in the frequency range of roughly 10 Hz to 1 kHz, ideal for detecting mergers of stellar mass black holes and neutron stars. However, many other astrophysical and cosmological sources lie outside this range. Space-based observatories such as the Laser Interferometer Space Antenna, LISA, will open access to millihertz frequencies, allowing the detection of gravitational waves from systems with much longer orbital periods. These include supermassive black hole binaries, extreme mass ratio and spirals, EMRIs, in which a stellar mass compact object spirals into a supermassive black hole, and even ultra-compact white dwarf binaries within our own galaxy. LISA's 3 spacecraft will orbit the Sun in a triangular formation separated by 2.5 million kilometers, enabling unprecedented sensitivity to slow, massive events and probing the formation and evolution of galaxies over cosmic time. In parallel, proposed pulsar timing arrays, PDAs, such as NNOGrav, EPTA, and PPTA are searching for nanohertz gravitational waves by monitoring the precise arrival times of radio pulses from millisecond pulsars scattered throughout the galaxy. Tiny shifts in these arrival times may reveal a background of gravitational waves produced by supermassive black hole binaries in the final stages before merger, spread across cosmic time. In 2023, tantalizing evidence of such a background was reported by multiple PDA collaborations, potentially representing the first step toward gravitational wave cosmology at extremely low frequencies. At the other end of the spectrum, high-frequency gravitational waves, those above the kilohertz range, are predicted in certain models involving exotic phenomena like oscillating cosmic strings, primordial black hole evaporation, or early universe phase transitions. Though current detectors are not yet sensitive to these frequencies, novel concepts like resonant bar detectors, superconducting cavities, and optomechanical sensors are being explored to push detection limits into this challenging domain. The multi-band approach to gravitational wave astronomy, combining observations from ground-based, space-based, and PDA detectors, will allow for the tracking of inspiraling systems across different frequency regimes. A binary of intermediate mass black holes, for example, might be observed years in advance by LISA as it slowly spirals together, with the final seconds captured in detail by LIGO or Cosmic Explorer. This synergy enables long-term study of individual systems and opens the door to precision tests of gravitational dynamics, including energy loss mechanisms, orbital eccentricity, and precession. Gravitational wave observations are also being integrated into early warning systems for cataclysmic cosmic events. In cases where signals from neutron-star mergers are detected in advance of the final collision, telescopes can be directed to observe the electromagnetic counterpart at the exact moment of impact, capturing transient phenomena like kilonovae or short gamma-ray bursts in real time. This real-time coordination between observatories, known as multi-messenger alert networks, is transforming our ability to study dynamic events as they unfold. As gravitational wave astronomy matures, it is also playing a central role in addressing some of the deepest philosophical and scientific questions about the nature of the universe. One of the most profound implications of this field is its ability to offer a direct probe into regions of spacetime that are otherwise invisible, such as the interiors of black hole event horizons or the moments just after the Big Bang. Gravitational waves do not scatter, absorb, or reflect like electromagnetic waves, they pass through matter and radiation almost unhindered, making them perfect messengers from the most extreme and hidden corners of the cosmos. For example, black hole mergers, especially those involving high-mass or spinning systems, produce waveforms that encode rich information about the curvature of spacetime in the strong field regime. Careful analysis of these signals allows researchers to test the no-hair theorem, a key prediction of general relativity stating that black holes are fully described by just three parameters: mass, spin, and charge. If deviations from the predicted waveforms are observed, such as echoes, ring-down anomalies, or unusual harmonics, it could point to quantum effects at the event horizon, or even to entirely new states of matter or spacetime, like gravastars or firewalls. Additionally, gravitational wave detectors may one day confirm or refute the existence of primordial black holes, which could have formed from density fluctuations in the very early universe. If detected, these objects would not only provide a new window into the high-energy physics of the inflationary epoch, but might also help solve the dark matter mystery, depending on their abundance and distribution. Current observations have placed constraints on the population of such black holes, particularly in the mass range where they might contribute significantly to the dark matter content of the universe. In the broader cosmological context, the detection of a stochastic gravitational wave background, a diffuse hum generated by countless unresolved sources throughout cosmic history, would provide a form of gravitational wave, cosmic microwave background. This background could carry signatures of phenomena such as inflation, topological defects like cosmic strings, or first-order phase transitions in the early universe, which might have occurred as the fundamental forces separated during symmetry breaking. These relic signals would offer an unprecedented look at the universe's first microseconds, well beyond the reach of photons or neutrinos. Gravitational wave astronomy also forces a rethinking of the concept of observation itself. Unlike traditional astronomy, where we observe light emitted by matter, here we are detecting distortions of the medium of existence, spacetime. This raises philosophical questions about the nature of reality, information, and causality. We are not merely seeing what happens to matter in space, we are listening to the dynamic vibrations of space itself, caused by cosmic events often billions of years and light-years removed from our present. The collaborative and international nature of gravitational wave science is another hallmark of the field. Detectors across continents are coordinated to maximize sky coverage and localization precision. When an event is detected, alert systems notify a network of ground and space-based observatories to begin rapid follow-up. The scientific return is distributed globally, and the open sharing philosophy has accelerated progress, innovation, and public engagement. The field has also sparked massive public interest, with gravitational wave events becoming headline news and inspiring a new generation of physicists, engineers, and data scientists. The educational and cultural impact of gravitational wave astronomy cannot be understated. The poetic nature of listening to spacetime itself has captured the imagination of not only scientists, but also artists, philosophers, and the general public. Gravitational waves have become symbols of a deeper, hidden reality, one where the universe is not a static backdrop but an active, resonating structure, vibrating with the memory of ancient cataclysms. These ideas are reshaping our collective worldview, bridging the gap between hard science and the human quest for meaning in the cosmos. In terms of technology, the pursuit of gravitational wave detection has driven advancements in multiple domains. To isolate the infinitesimal signals from background noise, researchers have developed techniques at the very limits of measurement, exploiting quantum squeezing of light to reduce photon-shot noise, using cryogenics to minimize thermal motion in mirror suspensions, and deploying artificial intelligence to classify complex data in real time. These innovations are not limited to astronomy, they find applications in other precision fields such as quantum computing, materials science, and navigation systems. Looking ahead, gravitational wave astronomy may even play a role in planetary defense and space exploration. If ultra-sensitive detectors are placed in space, such as LISA Pathfinder successors, or moon-based observatories, it may become possible to monitor subtle gravitational disturbances in near-Earth space, potentially improving our ability to detect massive fast-moving objects or explore gravitational anomalies near large planetary bodies. On interstellar scales, the technology used in gravitational wave observatories could inform future efforts to detect exotic propulsion systems or artificial gravitational signals, should they exist. There is also the tantalizing possibility that gravitational wave astronomy might eventually uncover evidence of non-natural or advanced phenomena. While highly speculative, the idea that extremely advanced civilizations, so-called Kardashev Type 2 or 3 societies, might manipulate spacetime or generate detectable gravitational disturbances as part of their technology has entered the realm of scientific discourse. Gravitational waves could serve as the ultimate dark broadcast, a potential medium for transmitting information across galactic distances with minimal attenuation, bypassing the limitations of electromagnetic communication. At the heart of all this lies a profound truth: gravitational wave astronomy has extended the human senses into a domain that was once thought inaccessible. We now observe not just the light of the stars, but the undulations of the cosmic sea itself. Every new detection carries with it a story billions of years old, a tale of creation, destruction, and rebirth, encoded not in light, but in the trembling of existence. The universe, once silent, now speaks in waves. And we are learning, at last, how to listen. As this field evolves, gravitational wave astronomy is increasingly intertwined with the grand project of unifying physics. One of the most ambitious goals in theoretical physics is to reconcile general relativity, which governs the macroscopic world and the structure of spacetime, with quantum mechanics, which rules the microscopic domain. Gravitational waves may be the key to bridging this divide. By observing black hole mergers and neutron star collisions, natural laboratories of extreme density, curvature, and energy, physicists hope to find clues about the quantum nature of gravity itself. In particular, the merger ring-down phase, the echo that follows the coalescence of two black holes, offers a potential window into quantum gravity. If spacetime is fundamentally discrete or if black hole interiors deviate from classical predictions, subtle modifications might be encoded in the waveform. Hypothetical phenomena such as Planck scale echoes, gravitational wave memory effects, or deviations from the predicted quasi-normal modes could signal the presence of new physics. These observations could test models like loop quantum gravity, string theory, and emergent gravity, which aim to describe spacetime at its most fundamental level. Gravitational wave astronomy also intersects with high-energy particle physics. Certain theories predict that phase transitions in the early universe, analogous to water freezing or boiling, would have generated a stochastic background of gravitational waves. For instance, in models involving electroweak symmetry breaking or grand unification, such transitions could have been strongly first-order, creating bubbles of new vacuum that collided and released gravitational radiation. The detection of these primordial waves would not only reveal the energy scales of fundamental interactions far beyond current colliders, but could also shed light on the baryon asymmetry of the universe, that is, why matter vastly outweighs antimatter. Another avenue of research involves cosmic strings, hypothetical one-dimensional defects in spacetime that could have formed during symmetry-breaking events in the early universe. These strings, if they exist, would generate gravitational waves through oscillations, cusps, and loop collapses. Detecting such signals would not only confirm the existence of new topological structures, but would offer insights into field theories operating at energies unreachable by any terrestrial experiment. In the coming decades, coordinated efforts across observational and theoretical fronts will deepen our ability to interpret the gravitational universe. International consortia are designing next-generation ground-based observatories, such as the Einstein Telescope in Europe and the Cosmic Explorer in the United States. These instruments will be 10 to 100 times more sensitive than current detectors, with the ability to observe mergers from the dawn of star formation and to detect binary systems well before coalescence. Their improved angular resolution and event rate will make gravitational wave astronomy a high-precision, high-volume science. Meanwhile, the planned launch of LISA will open up a new frequency band and allow scientists to detect gravitational waves from sources that are inaccessible from Earth. Among the most anticipated sources are extreme mass ratio in spirals, EMRIs, where a stellar mass object orbits deep within the gravitational well of a supermassive black hole. These objects complete thousands of orbits before plunging in, and their emitted waves trace the detailed structure of the black hole's spacetime, providing one of the most powerful tests of general relativity ever devised. The promise of detecting extreme mass ratio in spirals, EMRIs, is especially compelling because these systems function as precision probes of spacetime geometry. The small object, typically a neutron star or a stellar mass black hole, spirals into a supermassive black hole over thousands to millions of orbits, emitting a continuous gravitational wave signal. Unlike the short-lived signals from stellar mass mergers, EMRIs evolve slowly and encode intricate information about the central black hole's mass, spin, and multipolar structure. This makes them powerful tools for testing the Kerr hypothesis, which asserts that all astrophysical black holes are described by the Kerr solution of general relativity. Any deviation from the expected waveform may hint at the presence of new physics, such as modifications to gravity, the influence of dark matter halos, or exotic compact objects mimicking black holes. In addition, multiband gravitational wave observations, combining data from space-based and ground-based detectors, will soon allow astronomers to track binary systems over much longer periods. For example, a binary black hole system could be observed by LISA during its slow in-spiral phase, then later by LIGO or Cosmic Explorer during the final seconds of its merger. This long-term monitoring provides an unprecedented opportunity to study the full life cycle of gravitational interactions, from gentle spirals over years to violent coalescence in milliseconds. It also allows for predictive astronomy. Knowing when and where a system will merge enables targeted electromagnetic observations of the final event, boosting the potential for multi-messenger discoveries. Multi-messenger gravitational wave astronomy is already revolutionizing our understanding of the process nucleosynthesis, the formation of heavy elements through rapid neutron capture. The 2017 detection of GW170817 and its associated kilonova provided direct confirmation that neutron-star mergers are major sites of this process. Observations of the optical and infrared emission from the radioactive decay of heavy nuclei showed that elements like gold, platinum, and uranium were produced in enormous quantities, linking gravitational waves to the cosmic origin of the periodic table itself. Future detections will refine our models of how matter behaves under the most extreme densities and temperatures, and will clarify the role of mergers in enriching the interstellar medium. Another area of growing importance is the study of environmental effects on gravitational wave sources. While many binary systems evolve in relative isolation, others may reside in dynamic environments like active galactic nuclei, AGN, disks, dense star clusters, or galactic centers. These environments can influence binary formation rates, alter orbital dynamics, or induce rapid mergers. For instance, gas drag in AGN disks can accelerate in spirals or even align black hole spins, while gravitational interactions in star clusters can lead to eccentric mergers. These signatures, eccentricity, spin precession, or unusual mass ratios, can be imprinted in the gravitational waveform, providing clues about the astrophysical context of each event. Furthermore, the increasing precision of waveform modeling is allowing scientists to extract subtle features from noisy data. Numerical relativity simulations, which solve Einstein's equations for merging compact objects, are being combined with perturbation theory and machine learning to produce accurate waveform templates. These templates are essential for matched filtering, the technique used to identify signals buried in detector noise. As the catalog of detected events grows, so too does the statistical power to test population-level properties, the distribution of black hole spins, the rate of mergers across cosmic time, and the evolution of stellar populations in different galactic environments. As the field matures, population synthesis and gravitational wave demographics are emerging as major themes in gravitational wave astronomy. With each new detection, researchers gain better insight into the life cycles of massive stars, the influence of metallicity on black hole formation, and the role of binary interactions such as mass transfer, common envelope evolution, and tidal effects. By comparing observed merger rates and properties, like masses, spins, and redshifts, with predictions from stellar evolution models, scientists can constrain the physical processes that lead to compact binary formation. This includes determining whether most binary black holes arise from isolated binary evolution in galactic fields or from dynamical encounters in dense environments such as globular clusters, nuclear star clusters, or young stellar associations. In particular, gravitational wave observations are beginning to explore the mass gap problem, two mass ranges in which compact objects were previously thought to be rare or absent. The first is the lower mass gap, between the heaviest known neutron stars, 2.2–2.5 solar masses, and the lightest black holes, 5 solar masses. The second is the upper mass gap, between 50 and 130 solar masses, where stellar evolution models predict that parent-stability supernovae should prevent the formation of black holes. Yet LIGO and Virgo have detected mergers involving objects in both mass gaps, challenging existing theories and hinting at alternative formation channels, such as hierarchical mergers, where a black hole formed in a previous merger becomes part of a new binary. The detection of intermediate mass black holes, IMBHs, in the range of 100 to 10,000 solar masses has become a primary scientific target. These objects may form through runaway collisions in young star clusters or via successive mergers, and their existence would help bridge the gap between stellar mass and supermassive black holes. A confirmed population of IMBHs would also provide clues to the seeds of the first quasars in the early universe, potentially resolving long-standing puzzles about how supermassive black holes grew so rapidly in the first billion years after the Big Bang. On the cosmological front, gravitational wave standard sirens continue to offer a promising route to resolving the Hubble tension, the discrepancy between local measurements of the universe's expansion rate and values inferred from the cosmic microwave background. Unlike electromagnetic standard candles, gravitational wave sources do not require calibration against intermediate distance indicators, making them ideal for anchoring the cosmological distance ladder. With enough well-localized binary neutron star mergers, especially those with electromagnetic counterparts or host galaxy identifications, scientists can build an independent and increasingly precise Hubble diagram, probing the nature of dark energy and testing for deviations from the lambda CDM model. Moreover, gravitational wave observations are starting to touch on the dark sector of the universe. Some speculative models suggest that black holes might interact with dark matter in non-trivial ways, through accretion, drag, or even conversion into exotic compact objects composed partially or entirely of dark matter. In dense regions such as galactic centers or early halos, dark matter spikes may influence merger rates or modify waveforms in detectable ways. Additionally, certain ultralight bosons, predicted in string theory and other extensions of the Standard Model, can interact with rotating black holes via superradiance, extracting energy and forming gravitationally bound clouds that emit nearly monochromatic gravitational radiation. The non-detection of such signals has already placed constraints on the masses of these hypothetical particles, and future detectors may either tighten these bounds or make a discovery. Beyond the detection of individual events, the future of gravitational wave astronomy includes the ambitious goal of constructing a global gravitational wave map, a sky-wide picture of the gravitational universe, akin to the cosmic microwave background in electromagnetic astronomy. As the number of detections grows into the thousands and beyond, and as detector networks expand in sensitivity and coverage, it will become possible to statistically reconstruct the distribution of gravitational wave sources across the sky and throughout cosmic time. This will allow researchers to trace the evolution of structure formation, study the merger history of galaxies, and understand the role of compact binaries in the assembly of cosmic environments. Crucially, gravitational waves can travel from regions that are inaccessible to light, including those behind thick layers of gas and dust, deep within stellar interiors, or hidden in the dark outskirts of galaxies. This gives gravitational wave astronomy a unique advantage in studying obscured populations, binary black holes in dusty starburst galaxies, neutron star mergers in metal-poor dwarf galaxies, or events occurring during the epoch of reionization. These insights complement electromagnetic observations and enrich our picture of the universe's formation and evolution. In terms of global collaboration, gravitational wave astronomy exemplifies the spirit of open, multinational science. The current generation of detectors, LIGO in the United States, Virgo in Italy, CAGRA in Japan, and the upcoming LIGO India, forms an interconnected network that triangulates signals and improves source localization. Future upgrades, such as LIGO Voyager and the Einstein telescope, will push detection thresholds even further, while space-based missions like LISA will extend our reach to entirely new classes of sources. Pulsar timing arrays will continue to develop as radio astronomy advances, offering another complementary method of listening to the gravitational universe. Together, these systems form a gravitational observatory spanning the entire sky and a vast range of frequencies, from nanohertz to kilohertz. The diversity of gravitational wave sources is also expected to grow. Beyond black hole and neutron star mergers, possible future detections include core collapse supernovae, which may emit gravitational waves depending on asymmetries in their explosion mechanisms. Rotating neutron stars with slight imperfections, known as mountains, that can produce continuous wave signals. Post-merger remnants, such as hypermassive neutron stars or magnetars, which may briefly survive after a neutron star collision and emit complex gravitational waveforms. Cosmic strings and domain walls, remnants from early universe symmetry breaking, which may produce bursts or a continuous background. Primordial gravitational waves from inflation, the ultimate goal for understanding the universe's birth. Moreover, gravitational wave data is being used to test the constancy of physical laws over time and space. By comparing how gravitational waves propagate through different regions of the universe, scientists can search for variations in the gravitational constant, test Lorentz invariance, and constrain models that include extra dimensions or violations of the equivalence principle. These tests are conducted at energy scales and regimes that are otherwise unattainable, offering a unique probe of the very foundations of physics. In a broader human context, gravitational wave astronomy reflects a shift in our cosmic perspective. We are no longer passive observers of light from distant stars, we are active listeners to the movement of space itself. This transition parallels the historical moment when radio astronomy first revealed an unseen sky, or when X-ray telescopes unveiled violent cosmic processes. Today, the universe is singing a new song, and for the first time in history, we can hear it. As gravitational wave astronomy continues to unfold, its integration with other scientific domains becomes increasingly vital. This interdisciplinarity is not only expanding the horizons of astrophysics and cosmology, but also transforming fields such as nuclear physics, quantum optics, data science, and fundamental theory. The gravitational wave revolution is more than a technological triumph, it's a conceptual shift in how we perceive and study the universe. In the realm of quantum science, for example, gravitational wave